Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 1539, Kth Missing Positive Number. After that, we'll go over an actual variance that Meta asks. Overall, both problems are tricky brain teasers, but believe it or not, there is intuition behind it. By the end of the video, I promise you won't have to rote memorize it anymore. Let's start. The problem statement is short and tidy, exactly how I like it. We're given an array of positive integers sorted in strictly increasing order. We also have an integer k. We want to return the kth positive integer that is missing from this array. My first reaction is, okay, not too bad. But to make sure we understand what we're being asked, let's go over a few examples. Here's our array of the given positive integers. If we had a k of, say, 6, then that means we have to find the 6th missing positive number. But how do we know what the 6th missing positive number is when we don't even know what the first missing number is, or the second for that matter? You're right. Let's work our way up to the 6th one. It makes sense to do so from left to right. The first missing positive number is 1 because duh. The second missing is 2. The third missing 3. Clearly we already have a 4, so we don't count it. The fourth missing is 5. Fifth missing 6. We have a 7, 8, and 9 already, they're not missing. And finally, we arrive at the 6th missing number of 10. This is our answer. This is what we return. You may be curious, what if k was something like this, an 8? Well, we'd continue our workflow. If 10 was the 6th missing number, then it's reasonable to say that 12 is the 7th missing, and thereafter, 13 would be the 8th missing. That'd be our result. All right, let's crank it up a notch and try to think of a more programmatic approach. This is our example array and apparently a k of 5. Remember the walkthrough just now? We wanted the kth missing number somewhere amidst our array. But to know that, we must know all the missing numbers leading up to the kth one. I hope this arrow reminds you of a for loop. And indeed, we have to traverse left to right, and on each given iteration, figure out the number of missing numbers so far. On the first iteration, we have a 3. It doesn't take a genius to know that there are 2 missing numbers before it, the 1 and 2. Moving on to index 1, we have a 5. There are a total of 3 missing numbers to its left, the 1, 2, and now the 4. But wait, we're supposed to be doing this programmatically. How do we intuitively know that there are 3 missing numbers? Let me show you the intuition. First, by asking, how many positive numbers are there smaller than our 5? Easy, that's 4. 1, 2, 3, and 4. We can easily know this by doing 5 minus 1 to get 4 numbers. Great. Now, of these 4, how many numbers are already included and thus not missing? It's 1, it's just integer 3. Therefore, we can minus by 1 to get a total of 3 missing positive numbers. You may be wondering, where the heck did I pull this 1 out of? I must remind you, we're on index 1. This literally tells me there is 1 number before. And as a last note, we only found 3 missing numbers, not the desired 5. 3 is indeed smaller than 5, so let's keep going to the right. Where now we have a 6. We still have 3 missing numbers. As to how we figure this out, we again ask ourselves how many positive numbers are there leading up to this 6? Easy, that is 5. 1, 2, 3, 4, and 5. We take the 6, minus 1 from it to get 5. How many of these numbers are not missing? 2 numbers, it's the 3 and 5. Thus, we can minus 2, as denoted by the current index we're on, to get 3 missing numbers. Verifying this, those missing positive numbers are the 1, 2, and 4. Not quite the 5th missing number, but we're going to get warmer, I swear. Let's move on to the next iteration, where we have a 10. To its left, how many total missing positive numbers are there? Well, we can use our previously defined logic. I'll put it here for reference. We subtract 1 from 10 because there are 9 positive numbers before 10. And then we minus the current index of 3 because there are 3 numbers not missing to its left, namely the 3, 5, and 6. Doing so, we'll get us 6 missing numbers. Let's check that. 1, 2, 3, 4, 5, 6. Yep, that's right. But let's not celebrate just yet. We found the 6th missing number of the 9, by the way. But remember, we wanted the 5th one, the 8. Sadly, we went too far to the right. In retrospect, we should have stopped at integer 6 in the previous iteration. Building on this idea, when we were at the first 2 iterations at the 3 and 5, we should have kept going to the right. And to be fair, we did. We didn't find enough missing numbers yet. Inversely, at the 10 and 13, we'd ideally go to the left towards our 6 because we would have found too many missing numbers. The opposite problem. Now, do these 2 innocuous arrows and their symbolism remind you of a particular search algorithm? If it does, you need to touch grass. But also, you'd be right. We can use the binary search algorithm to solve this problem. Of course, that'd be absolutely absurd. There's no way anyone expects us to do that in an interview. We'll disregard it. It's kind of like an out of sight, out of mind kind of thing, and continue our train of thought. If we could go back in time and stop at the right iteration, at the 6 here, then what would our logic even be to return 8, the kth missing number? Let's break this down. We knew the count of missing positive numbers to the left of our 6, and we found that using our helpful equation. Doing so got us 3 missing numbers. These 3. Now, how many missing numbers left over must we find? Well, if we found 3 so far, but we need 5, then that means we need to find 2 more missing positive numbers. Revealing the mathematics behind it reveals the following. Lastly, this tells us we want the 2nd missing number from our 6 to walk to the 7 and then 8. Therefore, we should add 6 to this 2 to get 8. And when you look at that, this is our answer. This is what we return. Of course, here's the code for it. Amazing job. This linear solution works fantastically. Binary search is nowhere to be found. Good. I despise it. Let's jump into the code. Alright, I'm happy to announce there is a faster solution that uses binary search. I couldn't be more joyful. Thankfully, we already saw the intuition behind it. We can run this search algorithm, and on any given middle index, we can compute the count of missing positive numbers to the left. For the 6 in this case, this will tell us whether to go to the left or the right in our binary search. Okay, so on the first iteration, we run our trusted formula, realize there are 3 missing numbers that is lower than our k of 5, so we'll have to go to the right in search of more missing numbers. Adjusting our pointers like so. Our middle pointer points to A10. Remember, using our formula gets us 6 missing numbers. That, oppositely, is higher than our k of 5. Let's go to the left. All this means is we have to reassign the right pointer to middle minus 1. And wait 1 second, our 2 pointers have crossed. That signifies to us that our search algorithm has finished. That's okay, because where our right pointer ended up is the exact number we wanted to land on, the 6, remember? Like we did in our linear approach, we can run our gauntlet of confusing arithmetic to get an answer of 8, the 5th missing number. A few things to note here. Why did we do our math using the right pointer? Seems random. That's a great question, but little did we know we just deduced lower bound binary search, where if the number of missing numbers is ever less than k, then we go right. Conversely, if the number of missing positive numbers is equal or greater than k, we go left. Do you see how with this logic we are biased towards the left? Going to the left means reassigning the right pointer to middle minus 1, which as we saw, crossed our pointers. Thus, if the right pointer is in charge of biasing to the left, then that is the pointer we'd like to use. Of course, there are more fine details, but that's the gist of it. Here's another note. Writing this formula in an interview is doable because surely after watching this video, it all makes sense. But nevertheless, it is time consuming. There are a lot of algebraic expressions. We'll make life better for our souls and simplify it. Let's take a look. First off, recall the distributive property from middle school where the multiplication of a -1 here distributes to these numbers. and thus takes priority over its addition and subtraction counterparts. Doing so will make array of r negative, as well as flip the sign of our -1 and negative right pointer here to positive. Of course, the first part of our expression remains the same. Allow me to rewrite that. Up next, let me ask you, what is the array at r minus array at r? 0, they cancel each other out. We can X that out, and we're left with k plus 1 plus r, which, by the way, is the same expression as k plus r plus 1. I just changed their order, but it won't affect the output because of the commutative property. I mean, 1 plus 2 and 2 plus 1 both equal 3, right? Now, perhaps the trickiest part, what is the right pointer plus 1 equal to? Let me repeat myself. What is the right pointer plus 1? It's equal to the left pointer. In our binary search, we stop the instant both pointers cross one another, so they'll always be one index away. Rewriting this gets us k plus left. That said, I'm very picky about this stuff, so let's switch the order once again to get left plus k, and ultimately that is much, much shorter than our original lengthy formula. The time complexity is log n because of our clever binary search, and the space complexity is big O1. We didn't need any external data structures, just pointers. Amazing, our brains are filled with the knowledge. Let's code this up before my short-term memory kicks in. Okay, let's initialize our two pointers, the left pointer, which starts at index 0, and the right pointer, which is at the last index. We just did it in the walkthrough, so let's return left plus k before I forget. Back to the main logic, we'll enter a while loop so long as both pointers don't cross one another. On each iteration, we'll calculate the middle index, which is right minus left, divided by 2 plus left. More importantly, we must figure out the count of missing positive numbers to the left. Recall our formula. It was array at middle minus 1 minus the index. Now, if we had too few missing numbers relative to our k, then we'll go to the right, assigning left to middle plus 1. Inversely, if we had the exact number or higher of missing numbers, we'll go to the left, reassigning right to middle minus 1. That's really it. You're a binary search master now. The variance layers on one little trick, nothing we can't overcome. Let's take a look. Welcome to the variance, where nothing changes except for one slight detail. We must return the kth missing number, yes, but starting from the leftmost number of the array. In the original LeetCode problem, we started counting the missing positive numbers from 1. But here it's from the leftmost number. I'll tell you right now, this changes our OG code, but not by much. It's not a complete overhaul, but it's also not the littlest change. Our math formulas just need to be tweaked here and there, so we'll slowly build the equation by going through an example. Let's check it out. This is our array, and we must find the kth positive missing number of 7 from the leftmost number, or in other words, our 4 here. We'll dispatch a binary search, where on each iteration, we'll similarly figure out the number of missing positive numbers to the left, for integer 11 in this case. As the how, let's bring back our equation from the OG problem. We'd like to reuse as much of it as possible, but we shouldn't just blindly use it. Let's inspect each symbol and use some critical thinking. The first thing we did remember was to get the number of positive numbers lower than our 11. To do that, we minus 1 from 11 to get 10. Verifying this, that's the 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That is not right. In the variant, we want to get the number of positive numbers lower than our 11, but equal or greater to our first element, the 4. Therefore, we shouldn't minus by 1, but rather by the leftmost element. Doing so gets us 7. And if you're a doubter, this is the 1, 2, 3, 4, 5, 6, and lastly the 7. Great. However, we want the missing numbers, so we'd like to exclude these 3 numbers, the 4, 8, and 10. meaning we can and should still subtract by 3, index 3 by the way, to arrive at 4 missing positive numbers. This is correct. And you know what? This formula is quite robust. Let's go through the rest of this example with it. We know that 4 missing numbers is not enough. We want the 7th one. Therefore, we'll go to the right of our search space. Doing so will land us at a middle index at 5 of the 13. Clearly, there are 4 missing positive numbers less than it, but starting from our leftmost element. Let's still use our equation as a sanity check. 13 minus 4 gives us 9 missing positive numbers. 9 minus the current index of 5 yields 4 missing numbers. Fantastic. 4 though is still lower than our 7. Let's keep going to the right. Our middle index is 6, which points to 18. Plugging our numbers into our formula, 18 minus the leftmost element of 4 minus an index of 6 is 8 missing numbers. Here's 4, that makes 8. How accurate. Turns out we found 8 missing positive numbers, but we want 7. We found one too many. Let's go to the left in our binary search adventure. We assign the right pointer to middle minus 1. Doing so makes us realize both pointers have crossed one another. We terminate our algorithm. Very much like the OG problem, having access to this right pointer, we are very poised to compute what the 7th missing number is. Allow me to re-walk you through the lengthy formula. Don't worry though, we'll thereafter simplify the expression into a more memorable one. From our right pointer, which points to this 13, how many missing numbers were there to its left? Well, recall it was 13 minus our leftmost element, the 4, minus its index 5 to get 4 missing numbers, these 4. That was denoted by an array of r minus array of the leftmost number at the 0th index minus right. So if we found 4 missing numbers, but we want the 7th one, then clearly we need to find 3 more missing numbers from our 13. In our growing equation, we can prepend it with a k minus. Lastly, we can simply add 3 to our 13 to get 16 as our answer. This is what we return. But let's not forget our formula. We tack on the array of r pointer and add it. We can verify our answer real quick. 5 is the first missing number, 2, 3, 4, 5, 6, and 7. Amazing. Obviously, this is the kind of math that makes your brain hurt. Let's make it smaller and break it down. Well, once again, apply the distributive property of this -1. -1 times array of r makes it negative, flips the sign of the array of 0 as well as the right pointer. Next up, what's array of r minus array of r? 0, they cancel each other out. This leaves us with k plus array of 0 plus r. I'm very nitpicky about the order. Just goes to show you what kind of person I really am. We'll rewrite this as array of 0 plus k plus r. Alright, I'm satisfied. We can commit this to memory. Anywho, the time complexity is log n because binary search stuff, and the space complexity is big O1, equivalent to the original LeetCode problem. Let's look at the code and modify our equations. You'll be glad to hear this is short and sweet. Here are the 2 lines of code we must modify with our shiny new equations. On each iteration of our binary search, we'll now compute the number of missing positive numbers from the leftmost element, so we'll minus by array of 0. And as for the very last change, once our binary search finishes, we'll return the result as the leftmost element plus k plus the right pointer. Thanks for having ears and using them to listen to what I have to say. I wish you luck on your interviews. Hi, you're the best. Did you know that? I knew that. And if you learned something today, please make sure you like, comment, and subscribe. Thanks.